While the singly linked list can be pretty simple in the case of a lot of the operations and is fast at most operations involving the head and the tail, it can be very weak in removing items from the tail in particular. It also can only be proceeded through forwards from the head onward, and you can never go through it backwards from the tail back from there. To solve both of those problems, we're going to look at a doubly linked list. A doubly linked list will look pretty similar to a singly linked list, other than that each node will have not just a next variable, but also a previous variable. So each node will be able to go back or forward from that location. This means that a lot of the code for it will be very similar to a singly linked list. The node class looks mostly the same. It has a head and a tail, and we can write some functions for adding at that head and tail that will look mostly familiar to us at this point, hopefully. Adding at the head, adding at the tail, and we'll keep going with getting the head, getting the tail. Remember that we're returning the data when we get the head and the tail here, though sometimes for testing purposes you might need to get the node itself out as well. Return, nope, head.data, and for the tail, we'll return tail.data. And we'll write our toString. It will actually look the same as the toString from the singly linked list as well. We create a variable. Let's first create a variable to return. And then we do our basic loop. Node cur equals head. While it's not null, we'll step through. Okay, this should give us some of our basic tests compiling at this point to be able to add at the head, add at the tail, and print out the whole list. So if there is no data in our list, we'll need to set up the head and the tail. As we saw before, you may want to create a nice constructor for your nodes that takes their data. Here I haven't done that just to save writing a bunch of other methods. If the head is null, then head becomes n, and tail becomes n, and we don't have to do anything else. To add when there is already some real node as the head will be mostly the same, except we have to consider the previous variables and make sure that those are valid for the nodes involved as well. So again, our inclination might be just to switch head to n and think now n is the head, but we'll lose track of our old head. So we do have to make the new head, n, point forward to the old head. So make n's next point to the old head. We also need to make the old head point back to n with its previous, so that if someone was going backwards through the list, they would be able to reach n, our new head. And we do all that before we set the head equal to n, the new node that we've created there. Just like before, adding at the tail will look mostly the same as adding at the head to start with. And if we're uncomfortable with saying if tail equals null to check empty list, if we're uncomfortable with saying if head equals null to check for an empty list, then we can just check if tail equals null. It's equivalent at this point if you've maintained a correct linked list where when it becomes empty, both the head and the tail become null. And then again, we need to change things so that the tail will point to n. But before we can do that, we need to make things so that n and the old tail point to each other correctly. So the old tail should point forward to n, and n should point backwards to the new tail, to the old tail. And this should work correctly for our tests here, where we add 7 as the head, then we sort of push it forward by adding 12 as the head, and that makes 7 the second data. Then we add 5 as the head, meaning it should be 5, 12, 7. And we add 10 as the tail, meaning we should get 5, 12, 7, 10. Let's run it and see if we do. So when we run, our get head gives us 5, our get tail gives us 10, and we see the whole list is 5, 12, 7, 10. Now let's work on being able to remove things from it, which in some ways should be simpler than removing from the singly linked list. The code may have a few extra lines to it in some places, but it should be quicker operation in that both should be able to be constant time now, O of 1 time, where the removing tail was not able to be O of 1 in our singly linked list. So they're void again, remove head, and remove tail. All right, and we remember we had that nice little trick for testing if it is empty or there is only one item. In both cases, we want us to result in an empty list at the end of doing our work here anyway. So if the head equals the tail and they are real nodes, that means there is only one item, and both head and tail should become null. If the head equals tail because they're both already null, well, marking them both null again won't do any damage. We'll stay with an empty list at the end of that anyhow. So it catches 2 important cases. Now before, we were able to just say head equals head dot next, and that stepped us past the old head, and we would never be able to reach it again. However, with a doubly linked list, we might still reach the old head by stepping backwards through the list. So when we mark head equals head next, we also need to make sure that that new head's previous does not point to the old head anymore. It points to null. Our head's previous should always point to null in this kind of list. The remove tail will actually be simpler than it was before because we have that basic case of resulting in an empty list. And then we can, just like we were able to move the head forward, we can move the tail back. Tail equals tail dot previous. That takes us to the one that came before, before our current head, and that will step us back. We also need to make sure that tails next equals null. Let's uncomment our tests for the removing of head and tail and try it out. All right, beautiful. When we run the first set of tests to add, we get that list that is 5, 12, 7, 10. Once we remove the head, the 5 should be removed, and once we remove the tail, the 10 should be removed. We see that now, that 12 is the head and 7 is the tail. Our list no longer contains those 2 other items. So a doubly linked list has a few more complications to it in making sure that our previous variables get set correctly in addition to our next ones. So both our add head and add tail will have 1 line extra to set previous values for some things. And our remove head and remove tail will be about as complicated as they were before for remove head, and simpler than it was before, and faster than it was before for removing the tail, because we don't have to traverse all the way through the list to find that node that comes before our current tail. we can just use previous to do that. That makes all of the basic operations of the linked list O of 1 here without any real problems.